we're going to go ahead and solve a fun problem involving pulleys and rotational dynamics. So what I encourage you to do, read this problem, go ahead and draw a free body diagram on your own piece of paper, pause the video, and then check back in once you've done that. Cool. So now that you've drawn a free body diagram, I'll go ahead and draw one too. So for these type of problems, I usually say the downwards direction is positive. So for this little mass right here, we have gravity acting on it, which will be mg, and then we have tension right here pulling upwards. Cool. This is the same string right here, so we'll have the same tension acting on this pulley. And then we'll also have force of gravity acting on that pulley, and then some sort of force from the hinge as well. Cool. So now what I'm going to go ahead and do, so for this problem, I want to find the linear acceleration. So anytime I want to find acceleration, I always think I'm going to use forces to solve it. That's a great way to set it out. So I'm going to go ahead and think about, are things moving linearly or rotating? So this thing right here, that is moving up and down. So that's linear motion. So I'm going to set up F net for that one. So for mass M, I'm going to say F net equals, let's see, what forces act on that? Fg minus tension. And again, I say that the downwards direction is positive. So F net is Ma, Fg is mg minus tension. Cool, I got that. I'm going to go ahead and just leave that there and then come back to it. Now let's go ahead and look at the pulley. So for this pulley, so is that pulley moving up and down or is it rotating? Okay, looking at that thing, it looks like that pulley is rotating. So we're going to have to use the rotational analog to F net equals Ma, which that is good old T net equals I alpha. So now let's go ahead and put in things I know. So torque net. So I know the forces acting on this thing right here to make it rotate. I know tension is on the outside applied tangentially. That'll make it rotate that direction, which I guess is counterclockwise, which we defined as the positive direction. I'm going to have one torque. It's going to be the tension times R. And again, I should put up here that torque is force times R. Cool. Is any other forces acting on this making it rotate? So if we had a string on the other side, that would make it rotate the opposite way, and that string would have a different tension in it, so I'd have to subtract T times R for the other one. But there's not another string in there. Let's see. Gravity is applied right on the center. So if you think of like a bike wheel, and you're applying a force right on the center of that bike wheel, is that going to make it rotate? No. So gravity doesn't provide any torque. Same with force of hinge. That's applied right at the axis of rotation, so there's no torque. Okay, cool. Let's keep going. Moment of inertia. So this is a cylinder, solid cylinder. And I know my moment of inertia for solid cylinders is 1/2 mr squared. Cool. So I is 1/2 mr squared. Alpha, I'm going to need to relate that to linear acceleration because that's what we want at the end. And I know A is equal to R times alpha. Someone would tell me A equals alpha, but whatever. You can use what you want. So I'm going to substitute this in. So this is going to be A over R. Cool. Now I always love simplifying things a little bit. So in R squared, R cancels. So we have T times R equals 1/2 MRA. Cool. And I'll be careful as I go. This pulley is mass big M, and then this little thing that's moving down is mass little m. So keep in mind those are different. Oh, keep going back to the pulley. One more R cancels out. So then we're just left with tension equals 1/2 MA. Cool. So now there's multiple ways you can do it. You can take this tension right here, and you can substitute that in and go ahead and solve away. One method I use, it's just my favorite method to solve problems, is elimination. So I'm going to go ahead and set that up because we have two equations and two unknowns. So tension is 1/2 MA. I'm going to add these two equations together. So on the left-hand side, we're going to have little ma plus 1/2 big Ma equals tension cancels. And then we have mg. Cool. Now let's substitute out an A. And then we'll have like a little m plus 1/2 big M equals mg. Cool. Now let's just go ahead and solve for A. So A is going to be mg over m plus 1/2 big M. And that is our good old answer. Cool. One thing I think of which is kind of fun. So, okay, big M pulley. If you made big M pulley disappear, so let's say that disappears, then that whole term, this right here would be just 0. So then you would just have mg divided by m, the m's would cancel, and then you would just be left with an acceleration of g, or 10 meters per second squared, which is what, if that pulley wasn't there, kind of like slowing it down, adding more inertia to the system, this little thing right here would just fall straight down. So it's cool with physics to always go back and check your work and think about the why behind it all. Cool. Well, thank you for watching.